far, we've looked at the characteristics of waves themselves. In this program, we're going to look at how waves affect technology and how, if they're not controlled, can cause problems, like this bridge in Tacoma, Washington, which was literally blown apart by the wind. Since that disaster, a new bridge has been built which does not sway as much and is still standing. Ramina Suafoa Suspasara is an engineer on the new bridge, and she explains why the old one went down.
The original Tacoma-Narrows bridge was nicknamed Galloping Gertie because it was known for its flexibility. It literally shook itself to death. As the wind velocities increased, since this area was known for its high winds, the frequency of the bridge changed. On a normal day, it was about 8 cycles per minute, whereas when the wind velocities increased, the frequency would increase. And ultimately, the wind caused the frequency to increase to 36 cycles per minute with a double amplitude of 3 feet, which means that the bridge was literally flapping in the wind.
Every object has a natural frequency. This is the frequency where vibrations and the waves they produce can have the largest amplitudes. Unfortunately, this bridge had several natural frequencies, and the wind activated them all. An object that's vibrating at its natural frequency can be kept vibrating for a long time with very little force. It's like pushing a swing. The swing moves at a natural frequency, in this case about 1 cycle per second. The amplitude, or how far the swing moves, can be greatly increased with a series of small pushes, but the pushes have to happen at the frequency of 1 cycle per second. In this way, pushes with very little force can produce extremely large amplitudes. That's why the wind was able to bring down the Tacoma-Narrows bridge. The pushes from the wind matched the natural frequency of the bridge. In other words, the bridge resonated with the wind. Like pushing the swing, a relatively small force activated waves with extremely large amplitudes along the length of the structure. In fact, you can even see this amplitude and the shape of the wave along the edge of the bridge. It was the size of this amplitude that destroyed it. In an earlier program, Doug Loesch described how wind produced natural frequency vibrations in this skyscraper. He also had a solution on the 63rd floor.
A building like Columbia Center vibrates or sways at its fundamental natural frequency, primarily caused by the wind, and that gives rise to accelerations in the building which can, under certain circumstances, be perceived by the occupants. There are 2 basic ways to control the level of acceleration. The first is to increase the mass and stiffness of the building, and that's not usually very economical. And the way that we undertook to reduce the perceived level of acceleration was to increase the damping value of the building. A steel frame is very springy and only has about 1% natural damping. That, in this building, would have resulted in accelerations that might be felt under certain conditions by the occupants. To increase that level of damping without increasing the number of steel members and thereby the mass and stiffness of the building, we provided these viscoelastic damping assemblies in the frame. There are 260 of these units, and they basically consist of layers of very highly specialized films sandwiched between steel plates. And the film is sheared between the steel plates as the frame moves when the building vibrates in the wind. And that causes the energy of vibration resulting from this motion to dissipate in the form of heat.
Damping tries to prevent resonance, but sometimes resonance is desirable, especially in wind instruments. The shape of the instrument is chosen so the instrument will have a natural frequency that matches the sound waves. The sound waves activate the cavity, which produces more sound waves of the same frequency. The result is a louder sound. We can see it here where the waves fit exactly within the length of the spring. Resonance is used quite successfully in exhaust systems that have shapes specifically tuned to the exhaust note of an engine. This improves performance because resonance reduces resistance in the tailpipe. It also makes the engine louder, which some people prefer. All waves affect each other when they interact. These waves reflecting off the wall meet the original waves coming in. At the intersection, there's interference. The result depends on what parts of the wave meet. If a crest of one wave meets a trough of another wave, the two being opposites will cancel each other out. This is destructive interference because the waves essentially destroy each other. If two crests or two troughs come together, they add to each other and create one large wave with an amplitude that is the sum of the amplitudes of the two original waves. This is constructive interference because the two waves construct a bigger one. You can see constructive interference in the water. Here, where there's a large wave, and you can see destructive interference here, where they've canceled each other out to make a flat spot. Constructive and destructive interference happens in all waves. With sound waves, it shows up as a... what?
Excuse me.
What? What's wrong, Peter?
You're too live.
I'm too live?
You're too live.
Well, what do you want me, dead? I feel all right.
No. Dead, we can make it dead too, but no, you're too live. Your voice is too much resonance in this studio.
Oh, there's too much echo?
There's too much echo, it's too much reverberation, it's destructive interference coming back from the walls to the microphone. Recording studios are built so that they have a wide variety of acoustical areas. They reflect sound, some absorb sound. In this case, it's a large room. It reflects a lot of sound. It bounces off the walls, the ceilings, the floor. But that's a good thing for violins and for horns and reed instruments. Wood instruments sound good in a resounding chamber like this.
So there's some kind of resonance or interference or things?
Yes, sound coming back. It's not interference on a negative way, but a positive way. It's the sound comes back and you like it. It sounds better. But for you to sound like this sounds like you're recorded in a warehouse. We have to make you a dead spot. So here's how we do that. So we'll take this gobbo. This sounds a little quieter, a little deader. Stay on the microphone and you'll hear how this sounds.
Okay, so if I read the script now, constructive and destructive interference. I guess it is,
It's
yeah. It's a lot
Okay,
closer.
now, we also have these sound absorbers, which we can put up like this.
Piece of foam.
It's a piece of foam.
But you're essentially making the room smaller.
Now try it.
Constructive and destructive interference happens in all waves. With sound waves, it shows up as echoes and dead spots. Hey, I think you're right. With a good understanding of natural frequencies, resonance, and interference, it should be possible to put vibrations and waves to constructive use.